Great. Well, it's 3:05, so it's my duty and pleasure to welcome Edison Thomaz this afternoon to give a talk to us on balancing performance and acceptability in real-world automated dietary monitoring. So without further ado, over to you, Edison.
Thank you so much. It's a real pleasure to be here this morning for me, this afternoon for you, and I wanted to thank you for inviting me to the seminar series. You know, this is great. I've been actually watching many of the videos myself, and so it's really great to be on the other side now and actually be here contributing our talk. Yes, so I'll be talking today about this challenge in automated dietary monitoring. Before I get into that, let me just tell you a little bit about the work that we do in our lab. So we're here at the University of Texas in the US, in the Department of Electrical Computer Engineering. And our research is in this space that we refer to as computational perception of human signals. And we take human signals quite broadly. You know, we think of human signals as behavior signals, emotional, physiological, social, contextual. And our work tends to be very human-centered. So we develop new sensors, we develop new computational methods, and we take an HCC sensibility to the way we do the way we do approach this work. And one of the areas that we really emphasize in our work is this space of sensing and quantifying human behaviors, especially in dynamic environments. And given the possible range of human behaviors, there's so many different types of activities and behaviors. We focus specifically on the ones that tend to be a little bit more health focused. And in this talk, I'm going to be talking about automated dietary monitoring. Now, as you are all aware, we have been able to track many types of human behaviors that have to do with physical activities and fitness with much success. We have lots of consumer products now that allow us to track our runs, our steps. We can actually track sleep quite well. But the space of dietary monitoring is still not quite as developed, and there's still many challenges. And of course, eating is a fundamental aspect of human life. We eat many times a day. It's a social activity, but yet we have so much trouble in being able to objectively capture dietary behaviors using computing technologies and sensors. So this is an area that's still very challenging. And when I talk about tracking dietary activities, I'm talking about detecting not just when you're eating, but also what you're eating, of course, and with whom, and what's the context of those kinds of eating activities. Now, historically, the way that this has been done, especially from the perspective of health researchers and those interested in tracking, say, nutritional patterns and so on, it's been through methods such as dietary recalls and food frequency questionnaires. Dietary recalls being, can you, for example, remember and write down what you ate over the last 24 hours? Food frequency questionnaires are more about general patterns. Do you usually eat fruits and vegetables, and how often do you eat fast foods, and those kinds of things. And these have been sort of the traditional instruments that researchers have used for many years, specifically in nutritional sciences and health behaviors and so on. And these are the instruments that have produced content that led to guidelines and so on about what people should be eating, and the My Plate guidelines here in the US about what percentage of your plate should be designated to fruits and vegetables and so on. Of course, over the last decades in smartphones, now we have many web-based tools and also mobile phone tools, that mobile applications that allow us to keep track of what we eat. And here are two popular tools, MyFitnessPal and also MealSnap. MyFitnessPal, you actually have to enter a lot of information manually, and there are these databases that allow you to link different types of food and content to nutritional information. And MealSnap is one where you basically take a photograph of whatever it is that you're eating, and the system tries to infer your meal. These are a bit better than having to keep track of everything on paper. Of course, you have your phone always with you. But in general, there's still many challenges. There are many validity problems, there are biases, there are memory recollection issues that come up with these self-report based approaches. And so there's a real need for more objective methods for dietary monitoring. I talked earlier about how in the space of dietary monitoring, there are many questions that one could ask, such as, when is it that someone is eating? But what people really think about is food recognition, right? What it is that an individual is actually consuming. And for many years, that has been the focus of the community. But I would say over the last 5 to 10 years, there's been a bit more emphasis on breaking down the problem into pieces. And there's been more emphasis on the eating detection part, just because it's such a foundational part of automating the dietary monitoring process. Before you can actually detect automatically, right, what it is that someone is eating, first you need to detect that they're eating. And so this has become sort of a very important building block. So knowing when is very, very valuable. And just knowing when is also valuable from a health nutritional perspective. So these days, there are many diets that are based on time restrictions. So eating certain foods only from, say 3 p.m. to 8 p.m. You can eat whatever you like, but you're not supposed to eat anything beyond those hours. There are some scientific studies that show that there are benefits to fasting and so on. So there's definitely lots of interest in being able to just detecting when a meal is consumed or food is consumed. And also in general, just in terms of interventions and coming up with just-in-time interventions for eating disorders, it's clearly very important to be able to detect when someone is eating or when someone is about to eat, so that you can perhaps come up with some sort of intervention or process to prevent that from happening in the future, or to nudge people towards some other activity that doesn't involve eating. So detecting when someone is eating is very also important, valuable on its own. Now, looking at some of the work that has been done like over the years, as you can see here, there are many different types of devices that have been tried. So you can see, for example, starting with Dong on the top left, you can see it's actually a smartphone tied to this person's wrist, keeping track of food intake gestures. Some approaches, early approaches using different types of accelerometers in different parts of the body. And some other ones here that are focused a bit more on the neck region. B from 2018, a device that's actually tracking some muscle activity sort of around the ear region. And finally, Bedri, which has recently published this work that involves a set of smart glasses with cameras and other kinds of sensors. Now, perhaps with the exception of Bedri here, which is basically just they put together just a set of smart glasses. Most of these are largely impractical for everyday use. I would say that most of you would agree that you probably wouldn't want to be walking around with these kinds of devices on you, especially the ones that are around your neck, that are compressed against the skin. It's just not something that you would want to wear on a day-to-day. And so the question then really becomes, right, how can we develop systems that balance practicality with performance? Obviously, these systems, many of these actually have reported some very good results in being able to detect when someone might be eating, and even determining different types of food categories and so on from the sensors. But you definitely want that level of performance, but you also need to marry that with practicality so that this becomes something that people use on a regular basis. You see sustained use and adoption over time. So in terms of optimizing for practicality, one of the directions that I've explored in my work, we've explored in our work in our group, is thinking about, again, how can we use these wearable devices that are now so pervasive and ubiquitous that we can perhaps piggyback on their functionality to do something different than what they were originally designed to do. And there's something different in this case being tracking what people eat. And a natural way of thinking about that would be with, for example, smartwatches in trying to detect different kinds of motions and gestures that have to do with food intake. And this is sort of one of the very first pieces of work that we did in this space back about 3, 4, 5 years ago. We were exploring this using smartwatches. And in this case, we were specifically trying to detect these food intake gestures. So food intake gestures just being, having some utensils and, bringing some food up towards your mouth and just trying to model this particular pattern. And then looking at the sequence and the sort of temporal density of these intake gesture inferences to then be able to say, okay, so it looks like there's been many of these food intake gestures within this period of time. This probably means that this person is having a meal. We ran lots of studies around this problem, and I'm just giving you some idea here of sort of the kinds of studies that we run in this particular case, but also in general. Right, we bring people into the lab. If it's a lab-based study, and we provide them with food, which is usually very easy when we're working with students. They're always ready for some free food. Not hard to recruit participants for that. And in this particular case, we basically just had an app that collected data from the watch. Nothing too fancy here. And then we brought people into the lab, and these were the kinds of experiences that people had. So, we had them eat, but at the same time we were talking to them. We tried to make this experience be as naturalistic as possible, even though they were, in a lab setting in front of their computers and all that. We used some pretty straightforward methods for analyzing the data and trying to model these food intake gestures. We used some descriptive statistics features, and we were using, in this case, random forests. This was a few years ago. I would say some of these more I guess exciting today deep learning methods and so on, they were not as emphasized as much, and also we didn't have as much data in this case, so we were using some more classical approaches on the machine learning side. We actually got some pretty good results, around 75–80% accuracy using an off-the-shelf smartwatch for this was actually quite compelling. But of course, this was for just detecting the food intake gestures. And then when we looked at the problem of trying to identify, for example, a meal such as lunch or dinner using these intake gestures, then we observed that, again, as I mentioned earlier, that we could look at how many intake gestures occurred throughout the day based on the raw sensor data from the watch. And we could see that there were more of these intake gestures, right, around times such as breakfast, lunch, and dinner. And we could use an unsupervised learning approach, such as a density-based unsupervised learning approach, to be able to find these clusters and then being able to pinpoint exactly when those meal activities were taking place. We collected some data in the real world, also for validating this. In addition to the data from the lab, we had 2 data sets, one with 7 participants over a day and one participant over 31 days. We had them use a wearable camera for capturing ground truth so that we could tell what they were doing out in the world. We had a tool that we used for annotating all the data that was collected, not only the photographs, but also the sensor data. And these are the results that we got for the data set of 7 participants over 1 day, 66.7 precision, 88.8 recall, and for the one with 1 participant over 31 days, 65.2 precision and 78.6 recall. So just bringing both of these together here, you can see that recall wasn't amazing, wasn't great, but it was fairly reasonable given the constraints of collecting data in the field and using the smartwatch. Precision was actually, even though it was stable between these 2 data sets, it was actually fairly low, right? And the reason why this was the case was because wrist motion signals are just very noisy, right? So there was a very high rate of false positives. A lot of things were perceived by the system to be eating activities, and so And that's a typical problem that really sort of plagues a lot of these systems, high rate of false positives. So the next iteration of this work was then thinking about how we could address some of these issues. And since people were already wearing these wearable cameras, we thought, okay, maybe we can have some visual analysis of the context to be able to tell whether it's an eating activity or if it's something else. So can a wearable camera help improve precision? This was the question that we asked. And in this case, with our camera setup, we had people wear this camera, as I showed you earlier. And these are the kinds of images that you can capture. So at the time, we're not capturing videos, we're just capturing photos. Say, for example, one photo every minute, capturing what people were doing. These are the kinds of images that could be captured with a setup like this. What did we find from this study? Well, of course, when you are capturing photographs in people's daily lives, for those who choose and would be willing to wear a camera, which is not a lot of people, there are obviously lots of privacy concerns that come up. So this was not a big surprise. So we had to remove many images from our data set due to privacy concerns, and this affected some of our results as well. But in the context of the problem itself, in terms of detecting eating activities, there were also some interesting challenges that we did not expect. So for example, here's a sequence of images that were captured as someone was driving, and except for one image, the second one from the left, in which you can see someone eating, it looks like it might be a biscuit or a piece of bread, you wouldn't be able to tell that an eating activity was actually occurring, right? Because you might not catch that moment with a photograph exactly when the food becomes visible. And so in this case, the recall actually dropped quite a bit. Recall being whether you can tell that someone is eating when they are actually eating, right? So this was difficult even for a human coder to actually go through these images and be able to identify that. Sometimes the evidence of eating was restricted to maybe one image if it was captured at all. Some other parameters that we were interested in at the time were, can we tell where people are eating things? And in many cases, it wasn't possible, just because, again, of the quality and the nature of these photographs. Based on the background, we could maybe tell. The photograph on the right, you could see that this definitely looks like an office type of environment, probably not someone's home. But in many cases, it was a bit challenging. There wasn't enough visual information in some cases. All right, so we had some challenges. We learned a few things from this work, and we decided to take our next step. What can we do moving forward? Looking back at the literature and previous projects, one of the things that obviously caught our attention was the fact that many of the approaches focused in this neck region, right? It's actually very compelling for dietary monitoring, because from here you can detect chewing. You might be able to detect different types of sounds that have to do with swallowing as well. So it's just in general just a very compelling region of the body for this type of sensing. But as I mentioned, for the form factor here poses a real acceptability challenge here. Talking about, again, this balance between performance and acceptability. Now, these are prototypes, and it doesn't really have to be this way, right? So even in industry now, we are now starting to see sort of this movement towards what some refer to as computational jewelry, embedding different kinds of sensors onto accessories that people wear on a daily basis. So these are actually photos from Fitbit. So Fitbit being the activity tracking company, they usually have those devices you wear on your wrist, but they have these other form factors. Or at least they've had at certain points in time where you could wear these necklaces and bracelets that actually don't look like a computing device in any way. And so can we perhaps build something that's a little bit more like this? And so we started looking at this problem, and we thought, okay, well, maybe what we can do is we can have a necklace, and it's important that it's loose fitting so that it looks more natural. And we don't want something that's compressed against the skin. But if it's not compressed against the skin, then it's a little bit harder for us to have a microphone in there to detect chewing sounds, and so on. So we thought, all right, if it's loose fitting, maybe what we can do is we can sort of observe the movement of the jawbone as it goes up and down, and perhaps that's an indication of mastication, of chewing. So this is what we did, and this is sort of the prototype that we built, and what we used as the primary sensor here was a light-based time of flight range sensor. And that was basically just looking at the distance between sort of the base of the neck and the jawbone. So as the mouth would go up and down, the jawbone would go up and down during chewing. You could detect that and hopefully be able to tell that eating is taking place. And so we had a Bluetooth module connected to that. We had an iPhone app that was actually was not an iPhone, it was just an Android app connected to that, and we were just collecting this data and trying to see if this was a signal that made sense for us to use. Here's some preliminary data, some fairly informal preliminary data that we collected. You can see here eating is up top, and at a certain point the signal becomes very deterministic. It's actually possible to discriminate that type of signal from some of the other signals. Obviously, sitting, there's not much activity, but brushing teeth and walking around and talking certainly is one that we're always communicating and talking all the time, moving our mouths, moving our jawbones, and so can we tell the difference between talking and eating? And it seemed like we were able to do that. So we pressed on. In this case, because we were just looking at this fairly simple pattern, we decided to make the system very lightweight and use just a threshold-based chewing detection approach. So we didn't even use a machine learning pipeline for this. It was basically just based on thresholds, which is also nice because it can also give us the ability to deploy this in a very lightweight manner using fairly small battery and so on. So there's some benefits to this. And in addition to this thresholding, we were just doing a little bit of clustering to be able to detect chewing activity, and then hopefully building up towards detecting meals and so on. We ran 3 kinds of studies in this project, part of this project. One was in the lab, which is the traditional bring people to the lab like I showed you earlier and give them food and ask them to perform a few different activities. I'll tell you a little bit more about the activities in a second. In the field also, where we basically just say, all right, here's the device, just go out into the world and do what you normally do, go to work, go home, play with your kids, do what you normally do. And then we came up with this approach in the middle that we called a controlled field study. And this one was one where we basically went out into the world with people for a meal with our participants. And so even though we were not in this super constrained setting of a lab, we were still following them, and we could still sort of keep track of what they were doing and whether they were eating or not. And we were making some notes, but it was very informal. We were basically just following along and chit-chatting with them as we were walking towards, say, an eating place, and then eating and so on. So we had 17 participants in the lab study and 15 participants for this controlled field study, and then the field study itself. And here's the breakdown of how many minutes these studies lasted. Different types of activities for them. So in both cases, we tried to combine eating activities with non-eating activities. Some of the non-eating activities were ones that we thought could be confused with eating activities, such as toothbrushing and so on. We provided participants with different kinds of foods. So here's also a breakdown of different foods. So soups and nuts, some foods that are more on the soft side, some that require more chewing. And we got some actually pretty good results in the lab. Usually in the lab, you get good results, right? So this is not too surprising, but it was encouraging. So 91.2% precision, 92.6% recall. Here's how these numbers were compiled from every one of our participants. Some of them did really well, some of them not so well. Actually, just one of them did poorly here. But overall, it's quite good. And the field studies were also okay, and you know, the completely in the wild study, you know, that's the really challenging one, because that's when people are really behaving like they normally do in the real world. And so we got some numbers there that were not as exciting as we were hoping, but we tried to understand what some of those issues were, and I'll tell you about them in just a moment. For the most part, people thought it was not too bad on a comfort scale. Obviously, there is still a bit of a stigma with a necklace device with a piece of electronics hanging from it. So so this was not great, but we were fairly certain that if, you know, in terms of performance, we could get to a good you know, a good measure, then we were fairly certain we could make the device look much smaller and much more like an accessory than a prototype. Here were some of the challenges that we faced. So there were two key challenges. One of them was light sensitivity. So the sensor that we used was a light-based time of flight type of sensor. And so obviously, if you're in the dark, that worked okay. But if there was a lot of light, then the sensor would saturate. So if you're out in the sun, for example, the sensor had trouble. And so you can see here, we ran a study where we went to different locations, we controlled for the amount of light, and we measured light intensity, and we sort of were able to see when the sensor saturated. So this was an issue. An even more concerning problem was that we wanted this to be against loose fitting, and we wanted this to be more like a necklace and very lightweight. These are all you know, constraints or parameters that, you know, initially we thought, you know, these are obviously we want this to be just like a regular necklace. But there were some problems that came up with this. First of all, it was very light. So because of the fact that it was very light, you would move around the neck quite a bit. And so there was a lot of motion artifacts that we had to control for in this case. And the measurement had to be quite precise, because it was really sort of pointing, the sensor was really pointed at the jawbone here. And so it was actually quite challenging to get this one right. So this was what we started with. This was our original motivation, thinking about sort of tracking these jawbone movements. And you know, as I just mentioned, we had some issues with regards to this distance between the sensor and the jawbone, both in terms of the light sensing issue, but also the movement, the motion artifacts issue. So we thought, well, what about, and this is now where we're becoming a little bit more, perhaps a little bit trickier, but because we're moving away from just a sort of a regular accessory that you would wear. But what if we actually move the sensor all the way to the jawbone, just monitoring the jawbone? We have to make the sensor quite small for that. But you know, we know that the signal is rich in being able to discriminate eating from non-eating activity. So what if we actually had the sensor on the jawbone itself? So we decided to do that. And this is when we really started getting more into designing custom boards and actually trying to make it as small as possible. And our motivation there was, can we make something that would look like a Band-Aid that you would put on your chin that would be able to monitor these jawbone activities? And so just expanding this a little bit more so you can see in a bit more detail. Granted, this was not perfect, but we just wanted to do some tests to see whether we could do this. And so just in terms of the fabrication, there was nothing too special about the board that we built, but you know, it was a flexible board. We tried to be very efficient in terms of battery consumption. We use this MCU from Texas Instruments. You know, there's this IMU that's connected to it. It's, you know, provides you with wireless connectivity again. So that was nice. And instead of having to use a Band-Aid, we used this. It's an adhesive it's an adhesive, it's a medical adhesive tape that you can put on that makes the at least when you're not looking from underneath, you can't quite see as much that there is actually something attached to your jawbone when you have it on. So again, we ran studies to test this out in the lab and in the field. Same kind of approach in terms of detecting ground truth as well. So just a few more details on the activities that people did and the amount of time. So, you know, we had participants had conversations and walk around, work out a little bit, do some drawing, note taking, web browsing, all kinds of, you know, good variety of activities, not an extensive set of activities, but a good variety. We also, again, try to have a fairly large variety in terms of foods offered, from foods that are more liquidy, like soups, to things that are definitely crunchier, like nuts and carrots and other things. And in this case, we did use a machine learning pipeline, you know, fairly standard, normalizing the data, extracting frames, extracting features from those frames. And then we had, again, 2 levels of clustering, one using an unsupervised approach for detecting clusters and clusters of eating. And then we used a sort of a merging, conditional merging approach, just using some more of like a rule-based method in terms of the duration of each one of the chewing bouts to be able to detect these eating episodes. Again, most of the features were statistical features. I mean, we had some frequency-based features there with some FFTs, but overall, nothing too novel in terms of the features themselves. We in our validation, we had data trained with we had the model trained with data from the lab, and we validated it with data from the free living study. And we actually got some good results here. And we got 91.5% in the lab, and then 90.6% F1 on the free living study data. And this was with leave one participant out, which was a fairly good result. So with regards to this particular approach, we are still moving forward in terms of trying to make the sensor even smaller, so that you can maybe attach it to the jawbone and also different parts of the body that could be used even for other applications. And so this work continues in terms of measuring motion around the face. But one of the things that we decided to explore as well, which was fun and exciting, was the moment that we were able to make the sensor you know, below 10 millimeters, it got into this range of what many others have explored in the context of intraoral sensing, or ADM, which means having sensors that are actually inside the mouth. So we decided to explore this because up until now, our work had been primarily on the eating detection side of things. And we also wanted to see if we could make some inroads towards detecting different kinds of foods and so on. You see in some of this prior work, the work by Lee from 2013, you know, they have they suggest this approach in which you can see that the board is kind of embedded in a tooth, which seems a bit unrealistic. The one by 2018 by Tseng, it's one where this is mostly materials paper, so they were actually not interested in building a full system. Obviously, you know, there's no battery here, there's no nothing like that for powering it. So it was more just a proof of concept in terms of, like, can you detect different kinds of chemicals with sort of using a more passive approach. Obviously, we wanted to do more than that, and so we had a few other challenges. For us, some of the motivations here were, as I mentioned, being able to go beyond just detection, doing food type identification, but also thinking about using this as a general platform for sort of intraoral sensing. Right? If you can successfully have a computing sensing platform that's comfortable inside the mouth, can you detect other biomarkers of interest, you know, from saliva, cortisol, and so on? Can you detect different kinds of, you know, chemicals and nutrients from foods themselves? Can you detect the amount of sodium, and glucose and so on, right? From foods and from saliva itself, from different kinds of body fluids. Technically, there were many challenges that we had to tackle. Two of them were, how do you power the sensor, right? And how do you attach this sensor intraorally? How do you do this? So how do you power the sensor? So there's been some work that have looked into having a sensor, an active, powered sensor inside the mouth. And this is essentially what they did. They were just trying it out, and they had these wires coming out of the mouth, and they were obviously this was just a proof of concept. And we didn't want to do that. This is not our goal. We were really interested in thinking about how we could take these miniaturized sensors that we were building, and could build a self-contained system, self-contained in the context of being power, having sensing, having the computation, all that together, or at least being able to send the data out somewhere for collection. So this is not what we were going for. So we decided to use initially a battery that would also be inside the mouth. But this battery needs to be biocompatible. What happens if someone swallows lithium-ion battery? That's not a good thing. So we had to choose a biocompatible battery for this. So this was obviously the battery. Having a battery inside your mouth is not ideal, but at least we were able to have a solution for this. Then the second approach, or the second challenge, was how do you attach the sensor intraorally? So we tried a few different methods, and I'm gonna just show you one failed attempt and then what we decided to go with. But this is the failed attempt. So this was we decided to basically have these. We 3D printed these boards, and then we placed both the battery on one and our system board on the other, the battery and the system board, and we attached them around the one tooth that we chose in the back of the mouth, so that it wouldn't be as noticeable in principle, with dental floss. And so you can just imagine how difficult this procedure was for actually deploying the system, for testing it. It was hard enough just on our dental sort of prototype that we had, intraoral dental prototype probe that we had, and inside the mouth was even harder. So eventually we decided to abandon this. The copper wires that were connecting the battery to the board, they were also it was easy for them to break, and it turns out that it also wasn't very comfortable. You can see here that the battery itself was actually fairly large compared to the board, right? So talking about future plans, obviously one of the things that we were excited about thinking about is can we come up with some sort of power harvesting way of powering this sensor. But let me tell you about the approach that we decided to go with. And the approach that we used was a custom mold. So basically we built a mold and embedded the sensor inside it. And there were a few advantages to this. One of them was the mold was much more comfortable. It wasn't just some dental floss tied around some tooth with the battery and the board. So this was just something that you could just put on your mouth, and it was molded to your mouth, to your teeth. And you can see the picture on the picture on the top row here on the right, in the very front teeth. You cannot see the teeth very well, because there is actually this mold that's sitting on top of it. So even though the other two pictures look a little bit like maybe the sensor wouldn't actually be as comfortable, this mold wouldn't be as comfortable, it actually was not too bad. So how do you put together this mold? We use thermoplastic for it. So this is actually a pretty cool way to do it. So we can buy these beads of plastic that you can heat them up. You can heat them up in water, for example, and we can shape them into any form that we want. And then when we cool it, it solidifies and it becomes just one solid unit. So this is essentially what we ended up doing. So we had this board, and we embedded it into the sensor, and we tested it inside the mouth. So there were a few new components to this system compared to other ones. So this one, again, we're using a wireless MCU, but this was by Nordic and not Texas Instruments, so it was a little bit more efficient. We were collecting inertial sensor data, 54 hertz from this device. And this MCU had an internal sort of MCU temperature sensor that we actually appropriated for temperature sensing in general. And we used a non-toxic, non-inflammable coin cell battery for this. And let's have just a simple video here, just showing sort of it in operation. Obviously, you know, this was going to be inside the mouth, and so we needed to make sure that this was could operate in an environment with water and other kinds of fluids. So you can just see there both the temperature and the inertial sensor data. Now, the temperature sensor was very interesting because the temperature sensor is what we were hoping to use to be able to detect different kinds of foods. And I'll talk about that in just a bit. But here's just some of the preliminary data that we collected. So chewing, walking, and talking. Actually, there wasn't that much variation, you know, at least visually from these three different kinds of activities from the IMU data. Now, the temperature sensor was really great because we were really able to tell when we had cold foods and drinks in the mouth and hot foods and drinks in the mouth. There was a little bit of a lag from the time someone ate or drank something from the moment you would see that change in the sensor. But in general, it was okay. So given a longer span of time of say 5 hours, when someone would drink and eat something and so on, you could see some interesting patterns. So then the question became, can we actually use this to detect different kinds of foods, right? So different kinds of foods are eaten at typical serving temperatures. They demand more or less chewing. So can we use that to differentiate different kinds of foods? And so in the study, we picked 9 foods and we sort of separated them into different classes. And this categorization was based on sort of the percentage of water content on the foods, the serving temperature, and sort of chewing duration. And here's the results that we got. So we tested this with 4 participants. So this was something that we did over the last year. You know, in this world of COVID, it's a little bit hard to run a study in which we're putting sensors into people's mouths when we're all dealing with this pandemic. So we couldn't really get that many participants in this case, but this was a good proof of concept. So, and we tested the ability to differentiate different kinds of foods based on the accelerometer data alone, temperature data alone, and the accelerometer and the temperature. And these are reflected in these confusion matrices up top. So using the acceleration only, you know, we were able to get an accuracy of only 55%, temperature only 77.5%, but combining, you know, chewing activity with the temperature, that was the best result. As expected, we were able to tell these different food classes, 85% accuracy. And eating detection was also quite good, 93% precision and 96% recall. And the features that we used were, again, you know, fairly traditional features. There was nothing too fancy about them. Now, there's a lot that I can tell you about this work, and I can tell you about different directions we're going with this. Obviously, now we're able to make these very small sensors, but in the interest of time, I'll start wrapping this up so that we can have some time for questions and discussion. But you know, I welcome you to take a look at some of the publications that came out of this work. But just summarizing, right? So balancing performance and acceptability is really key to progress in automated dietary monitoring. I showed you in this talk, you know, a few different, you know, explorations, a few different things we've tried to sort of probe the space and be able to see sort of what are the boundaries in these different directions. Consumer wearables are practical, but they fall short in terms of performance. So being able to use something like an off-the-shelf smartwatch, or, you know, even you know, perhaps you know, these new headsets, earbuds are now coming with the sensors on them. You know, maybe they can be used to some extent, but to really reached the level of performance that's required for many, clinical applications, for many applications that really lead to substantial uptake, both from a research perspective, but everyday usage perspective in terms of personal informatics and keeping track of foods that you eat and so on. They're not quite there yet. We argue that it might be beneficial to think about how to develop more custom devices and actually try to make them aesthetically pleasing and embed them into other kinds of things and accessories that people wear. This is a promising direction, right? So trying to take these accessories that people already wear and sort of embed them with computing is something that we would like to continue to explore. And I think in the context of dietary monitoring, this can be sort of a fruitful direction, especially, as I said, when we can start to combine what we are calling now these micro wearables that can really open up new modes of sensing human behavior analysis, not only, as I said, for dietary monitoring, but also more broadly for other kinds of applications. All right, so of course, as I'm wrapping this up, I have to thank all of my students. They're the ones that are actually doing all this work. So we actually got to go out recently to an outdoor restaurant to celebrate one of my students' graduation. It was one of the first times that we were able to do this in many months. So it was very lovely, and it was great to see them all. So thanks to them, this work was possible. I have a webpage. Here's my contact information. You can head to it, click on publications, and you can see a lot of the work that we've done in this space. Pretty much every project that I described today is covered by a publication. So if you'd like more details, feel free to check it out. And I hope you can all come to visit us here in Austin, Texas at some point. If you come to the US, if you're in the US, we have this brand new building. We're starting to get more and more into the space of human-centered computing, ubiquitous computing. So please feel free to come visit us, and we'd love to have you here. All right, so I'm going to open up for questions now. If you have any questions, feel free to shoot, and I'll do my best to answer them. Thank you so much.
Great, thank you ever so much, Edison. That was great. I guess a sort of virtual round of applause from me, and I'm sure on behalf of everyone else in the audience as well.